Building designers can achieve big reductions in embodied carbon. Join Corporate Responsibility Officer Amy Hattan as she talks with technical experts about ways to reduce the negative impact of buildings on climate change. Here's how embodied carbon is a production of Thornton Tomasetti.
Hi, and welcome to episode 5 of Here's How Embodied Carbon. This series explores how engineers and designers can reduce embodied carbon, which is the emissions from the manufacture, transportation, installation, maintenance, and disposal of building materials, and minimize the negative impacts of buildings and other structures on climate change. I'm Amy Hattan, Thornton Tomasetti's Corporate Responsibility Officer. We're an international, multidisciplinary engineering and consulting firm committed to channeling all of our capabilities to tackle climate change. And we've been focused on embodied carbon for over a decade. I'm talking with technical experts from across the company about the paths they are taking to achieve the greatest reductions in greenhouse gas emissions. Today, I'm talking with my colleague, Emily Kunkel, a specialist in decarbonization strategies, about how carbon capture, utilization, and storage, or CCUS, can greatly reduce emissions from cement manufacturing. Hi, Emily.
Hi, Amy. I'm looking forward to talking about one of my favorite topics.
To help us to understand the role of CCUS in reducing the embodied carbon associated with cement, can you explain how this material is manufactured?
Sure. Cement is only 10 to 15% of the mass in a concrete mix, but it's responsible for nearly 85% of the global warming potential. Why? It's partly the fossil fuels used to heat kilns up to 2,500 degrees Fahrenheit. That's the temperature needed to form the clinker in cement. Fuel combustion accounts for about 40% of the overall carbon footprint of cement. Now, we can reduce these emissions drastically by choosing lower or zero carbon fuels, and we could potentially use electricity rather than combustion for the heat. But the other 60% of the carbon footprint, which are the emissions from the actual chemical process, will remain.
That's still a lot. We don't usually think about chemical reactions when we're considering how to decarbonize. How does the chemical process of cement production cause carbon emissions?
Cement is made from limestone, or calcium carbonate, which is a compound of calcium, carbon, and oxygen. When heated, it releases CO2 and leaves behind calcium oxide, or lime. Carbon emissions are a direct byproduct of calcination. So even if we electrify kilns, we wouldn't be able to even achieve a target reduction in total emissions of 50%.
So how do we fully decarbonize this industry?
This is where carbon capture, utilization, and storage, or CCUS, enters the picture. According to the Global Cement and Concrete Association, the single most impactful way to reduce carbon footprint in concrete is CCUS. The carbon capture process can remove up to 95% of CO2 from the flue gas generated at the plant. That CO2 that was previously sent up the stack into the atmosphere. This process could capture around 1 million tons per year from a single cement facility.
Wow, that's huge. With such a great opportunity to remove emissions, why don't we see CCUS in use with every facility?
Well, this kind of carbon capture is a very complex and expensive process. But the good news is CCUS has been proven at a similar scale to what cement kilns need. And some of the biggest producers, like Lafarge and Heidelberg, have already invested millions of dollars in doing preliminary engineering to implement carbon capture at some of their plants. So the wheels are in motion, but it could take a few more years until we can get CCUS up and running at these facilities.
Why should we implement CCUS instead of finding new materials that don't have such high inherent emissions?
We should still develop new materials. There's no question about that. But there's a lot of momentum behind the transition to CCUS. And there are several factors that play into that momentum. First, carbon capture has been investigated by the government for decades. It's ahead of the game and will likely be quicker to deploy at a scale than manufacturing a brand new synthetic cement. Second, With CCUS, we get the same exact cement formula we already know and love, with no change in performance at all. We won't have to do any new certification or durability testing like we would with new materials. Another advantage of CCUS is that the existing distribution and knowledge networks will remain in place. It will be the same cement being transported to the same set of ready-mix facilities that have the same know-how with the material. Finally, it's important that low-carbon concrete remain affordable. The U.S. government is supporting CCUS with billions of dollars in grants and tax credits. This will drive down the cost of implementation and limit any overall increase in the cost of cement.
It sounds like we might be seeing a lot more CCUS in years to come. Thank you, Emily, for expanding our understanding of how this technology can achieve large reductions in the embodied carbon footprint of concrete structures. Folks, there's more. Follow Thornton Tomasetti for more episodes of Here's How Embodied Carbon.